So, after 2 marathon lessons looking at curve sketching, this last lesson on curve sketching should be relatively short. Essentially, the idea is we want to look at using what we've learned about derivatives, first and second derivatives, to determine more details from a graph when we use technology. So for all these questions, I want to sketch something. I want to see a graph using technology, but then use what we know about derivatives to find out more about that graph. What do I mean by that? Well, we'll see. This won't take nearly as long as the other lessons. So what I have here are 3 graphs, but they're all related to one another. The graph in blue is f of x. So let me label that. Okay, that's our function. The graph in red is its first derivative. And the graph in green, the dashed graph, is the second derivative. So 3 different functions are all related. And as you can see, the various x-intercepts of all these functions I've labeled a through h. So each of these x-intercepts tell us something about function f. I mean, they're all the x-intercepts of the individual functions. But each of these intercepts tells us something with regards to function f. And that's what I want to do. So just by having these various points already graphed, what do they tell us? So for example, point A here. Point A is the x-intercept of the second derivative. And the x-intercept of the second derivative, that means that's where our second derivative equals 0. And that represents the inflection point for function f. So that point A is the inflection point, which means function f, if I look just right above it, right there, that must be an inflection point between where it's concave up and concave down. So even though it's hard to tell by just looking at function f, by looking at the second derivative, I can see when I'm less than a, my second derivative is positive, which means I know this is concave up. And when I'm to the right of a, my second derivative is negative, so I know this region here is concave down. Even though it's kind of impossible to tell that detail just by looking at function f in isolation. That's the idea for all of these. So A is an inflection point. OK, so let's work my way down the alphabet. B. Well, B is where my first derivative is 0. And where my first derivative is 0, that's a critical point. And that means I know if I look straight above at that instant, that's either a local max or a local min at that exact point. And again, I can tell roughly where it is, but if I just look at the graph of f, it's hard to tell where in this region is the highest point. I can tell somewhere in there's a highest point. But now I know by looking at these other derivatives that it must be exactly at where point B is. That must be the local maximum there. But in general, just by looking at the fact that I have a x-intercept right there, I know that point B is a critical point. Or maybe I'll say a critical number. But then in brackets, I said I know it's a, I can also tell it's a local max. Actually, to be honest, by looking at the, just by looking at the derivative, it is increasing on one side, it's decreasing on the other. Or I should say f is increasing on one side, f is decreasing on the other. And I know that because the derivative is positive to the left and the derivative is negative to the right. So that's how I know it must be a local max, even though I can kind of tell just by looking at the graph. So the idea it's a critical point is more important. Whereas A, again, is not a critical point. All right, C. C is the x-intercept of the function. What does that tell us? Well, honestly, that just tells us it's the x-intercept of function f. It tells us where function f is 0. So that's it. It's an important point for any function, the x-intercept. But, you know, it's just the x-intercept. I'm more interested in the others. And so D, that's again where my second derivative is 0. That's another inflection point, which means I know function f has an inflection point about right there. And by looking at this second derivative, it never comes back down at this point. It just keeps going up forever, which means there's no more inflection points. All right, E. E is another, sorry, let's look at E right here. In fact, E, F are, and, sorry, not E and F. Hold on, actually, you know what? I'm going to do this one at a time. I was able to get a little impatient, but I should have patience. So E, one at a time, is another critical point. It's where my first derivative is 0. Or say critical number. And in this case, notice for this particular, by looking just at the derivative, to the left of E, my derivative is negative. To the right of E, my derivative is positive. That means I know without even looking at function h, from the left of E, it's decreasing. The right of E, it's increasing. So I can tell that must be a local min. Although again, that last part of brackets is the least important part to me, because the whole idea is I'm looking at I have the graph of f anyway, so I can tell it's a local min. Now what about f? If we look at f, it is an x-intercept for function f. Okay, point f is a x-intercept of function f. But also, if I look at function f prime, my function breaks apart right there. I can see to the left it's going up. To the right, it's going down. So I know it not only is it the x-intercept of function f, it's also another critical point. Because remember, a critical point is where your derivative is either 0 or undefined. And what I'm seeing here is that my derivative is undefined at f. Looks like there's an infinite discontinuity for the derivative. And I can tell that actually, because if I just look at function f, there's a cusp right there. And so f is an x-intercept of function f, but it's also a critical point, because again, my derivative is undefined right there. So I'll say two things. It's a critical point, or say critical number, slash, it's also the x-intercept in this case. Remember again, critical number is where your derivative is 0 or undefined. Which leads me to the last two, g. G, a little more straightforward, another critical number. Also leads to a local min again. And lastly, h. That's just the x-intercept of the function f. So before I move on to the second and last problem, keep in mind the idea behind this was that all these points, a through h, the various intercepts of the function, the first derivative and the second derivative, these are all telling me what they tell us about with regards to function f. And so let's look at this. What I have here is a graph of 6 sine x minus x squared restricted from -5 to 3. And if I look at my restriction, it includes -5 and 3. So I'm just going to make a nice clear endpoint here and here. OK. So I want to use technology and derivatives to determine the various intervals of increase and decrease, concavity, and inflection points. Now if we look at this, I can tell roughly that it seems to be increasing from here to here. It seems to have a critical point here. It's hard to tell exactly what's going on right here. Then it seems to increase again. It definitely seems to have a maximum right here, and then it goes down. So I can tell roughly where it's increasing or decreasing, roughly. I can't tell where these points are exactly. In terms of inflection points, it seems to be concave down until about around here somewhere. Although it's kind of weird what's happening here. If I look at it in detail, it's hard to tell. Then it's concave up, and it seems to be concave down around here somewhere. And again, I can't really get more accurate, even if I had the graph in front of me. I can't really get much more accurate to know exactly where these, especially concavity, is without looking at the derivatives. Well, the good thing is, and this is function f, or this is just y. So I don't feel like writing that equation out. Let's use technology and the graphs of the derivatives to figure out more about this. So the good thing is the first derivative and the second derivative are quite easy. The first derivative is 6 cosine x minus 2x. And while I'm at it, the second derivative is going to be minus 6 sine x minus 2. So what I want to do now, again, is while I could algebraically solve for x and see if I can get there, the idea, that's not the point of this. The point of this is I now want to graph these derivatives and see what that tells me about this function I have sketched in front of, I already have drawn in front of us. So for this, I'm going to go to Desmos, and I want to look at function that's in blue. I'll call it function f, or 6 sine x minus x squared, and compare that to the first derivative first. All right, so first of all, here is the function I gave you, all shown on a grid. I'll kind of compress the scales a bit so it looks a little more, so it fits the space a bit better. Okay, and let me now show the first derivative. Here's my first derivative, which notice again, of course, it stops at the endpoints because my function is not defined beyond those endpoints. So first, where is my function increasing or decreasing? Well, my function is increasing anywhere my first derivative is positive. It's decreasing anywhere my first derivative is negative. And so, that point is pretty clearly where it's changing from increasing to decreasing. But notice right here is actually an interval between about negative 2.9 and negative 2.6, where my function is actually decreasing for some little interval. So I now know, since my derivative for that little interval is negative, I know if I look straight down, my function is actually decreasing for that little interval, which I can kind of tell now if I look at the details of this. But again, if I was just focusing on the graph, it would be hard to know that for sure. Now I know with absolute certainty. And so if I zoom out again a bit, all I really need to pay attention to are these x-intercepts. And this will tell me where my function is increasing or decreasing. I now know my function is increasing anywhere my derivative is positive. So from negative 5, which is an endpoint, to negative 2.938. Again, from negative 2.63 to 1.17. And that's it. That's where it's increasing. And then it's decreasing in the other intervals. All right, so let me write those numbers down, but the most important part's now done. And so clearly what I'm about to write down doesn't make any sense unless we are referencing that graph. So increasing. And keep in mind these are approximations. It's as accurate as that technology will, it's many decimal places it will give me. Hold on, I wrote that down wrong. Now I will say, looking at where it's increasing, these inequalities here, I'm missing another inequality right here. There we go. I mean, whether I show it like this or like this, it doesn't really matter too much because these are approximations. The only number here that's exact is that negative 5. So really, these are all approximations. So I'm not going to get hung up on that at all. Okay, and decreasing. Similar idea, where my derivatives was negative. And again, this is all the numbers I'm writing down are referencing back to the graph I had. And again, keep in mind, of all these values I wrote down for where it's decreasing, it's only 3 that's actually an exact value. All the rest are approximations. So again, whether we say less than or equal to or less than, it's kind of moot point. All right. So now, by going back to my graph again, I can tell roughly there's an inflection point around here somewhere and around here somewhere. However, now that I know it's increasing and decreasing a little bit right here, I know there must be some other inflection points around there. Or there may be, at least I should say. So that's it. I don't have to make any guesses. I can just go to Desmos, turn off my first derivative, and turn on my second derivative. And so for inflection points, which leads me to concavity, I just need to pay attention to these 2 points here. Those are the only 2 inflection points. And now I know exactly where they are. So I know it's concave up everywhere my second derivative is positive, so between negative 2.802 and negative 0.34. And I know it's concave down everywhere else. All right, so let me write that down. And like before, everything I'm writing down right now is meaningless without referring back to those graphs. And that means as well, I'll write these inflection points. Must be at where x is approximately negative 2.802 and approximately negative 0.34. And so keep in mind again, the idea behind this lesson was using what we've learned about derivatives to determine more details about graphs that we've graphed with technology. It's kind of the reverse of the last few lessons, where we use what we knew about derivatives to create the graphs. Now we have the graphs using technology, and we want to use first and second derivatives to determine, some of the more specific details about these functions. All right, so like I said, considerably less involved in the last few lessons, but I don't think I need to talk more than that. Oh, that's good.